Hello everyone, I am Giuseppe Parrella from University of Salerno, and in this presentation I will talk to you about our recent systematization of knowledge paper titled Gradient Inversion Attacks in Federated Learning. Let's start with a little bit of introduction about federated learning. Federated learning is an emergent machine learning paradigm that enables multiple clients to jointly train a machine learning model in a collaborative way without the need to share the raw data directly. As we can see in the figure, there are two main roles involved in this federation. The first type of actors involved are the clients. Typically, a federation includes multiple clients, which can also be heterogeneous devices, each holding a local private dataset that is never directly shared with any other party in the federation. Then the second type of actor in the federation is the central server, which acts as a coordinator, as an orchestrator of the training process. Typically, the central server does not own any additional datasets and has no direct access to the client's data. The training process in federated learning is performed over multiple iterations, similar to the centralized machine learning paradigm. And in each iteration, the central server selects a subset of clients and distributes the global model. In the first iteration, it may be a randomly initialized model or a pre-trained one. Then each client performs local training and sends back a model update. And the server collects and aggregates these updates to produce an updated version of the shared model. And this is the process that continues until the convergence is reached. A SoK federated learning is expected to provide stronger privacy guarantees since raw data never leave the client's devices. There exists a class of attacks that are called gradient inversion attacks, which aim to reconstruct the client's private data starting from the model updates sent during the collaborative training. As we can see with the two images A and B in the figure, a gradient inversion attack can even reconstruct an accurate approximation of the user inputs. In this work, we present a comprehensive systematization of knowledge of gradient inversion attacks in federated learning based on an extensive review of 107 publications published between 2016 and 2025. Our first contribution in this work concerned the definition of the threat model under which gradient inversion attacks can be performed. The main threat actor considered in almost all the works in the literature is the central server, and we observed that previous studies lack of a comprehensive systematic analysis of the threat model, as they usually provide only a broad discussion of threat levels. In our work, we identified 8 different threat models, and for each threat model we highlight the key knowledge and capabilities of the adversary. The first 5 threat models, which are labeled from A to E, involve a passive server that cannot interfere with the standard training algorithm in federated learning. However, this server may still leverage the knowledge that it naturally possesses due to its role in the federation. However, even a passive server may leverage some additional knowledge, such as surrogate data or statistics about client data distribution, to refine the input reconstruction, the input approximation process. In our evaluation of real-world applicability that you can find in the last column of the table, these two threat models are rated as 2 out of 3 stars, since in some scenarios it may be difficult to obtain such as surrogate datasets, or it may be difficult to have statistics about the client's data distribution. This is the case, for example, when batch norm layers are not used in a shared model, and the client does not share this kind of statistic with the server. This is common in federated learning, where batch normalization is often replaced with group norm layers. The last 3 threat models, labeled from F to H, involve a more powerful active server, which can also interfere with the training procedure, for example by manipulating the shared model sent to some clients during the specific training iteration. In these cases, the real-world applicability is rated as 1 out of 3 stars, as such active behavior can be detected, potentially leading to accountability issues and significant reputational damage for the server. Even under active threat models, the server may leverage surrogate data to perform more powerful gradient inversion attacks. Our second contribution concerned gradient inversion attacks, and we have categorized gradient inversion attacks into 3 main categories. In the figure we can see a graphical overview of the 3 main categories identified: the optimization-based attack, the generative model-based attacks, and the analytic-based attacks. If we focus on the first categories, we can find the optimization-based gradient inversion attacks. This class of attacks formulate the input reconstruction process as an optimization problem. In these approaches, additional knowledge from a surrogate dataset can be used in two ways, either as auxiliary regularization terms during the optimization, or by incorporating generative models, either interleaved with the optimization process or applied afterwards the optimization. Here we can see some takeaways that we have developed throughout our work on all the categories identified. And with respect to optimization attacks, we note how although optimization-based attacks lack of formal mathematical convergence guarantees, they often succeed in reconstructing client input quite accurately. However, the effectiveness of this class of attacks is highly sensitive to the experimental setup, including factors such as network architecture, network initialization, the training state, the batch size, and the training algorithm. In particular, nowadays, the federated stochastic gradient descent algorithm combined with ResNet architecture and small batch sizes represent the most vulnerable setup, especially under threat models D and D, where the adversary may leverage auxiliary knowledge, for example, from surrogate datasets. The generative model-based attacks are the second class of attacks that we have identified and incorporate generative models into the attack strategies in various ways. The most common approach illustrated in the figure is the subcategory of latent space optimization attacks, where basically the optimization problem is shifted from the input space to the latent space of a pre-trained generative model. The other two subcategories identified are the online optimization and the direct reconstruction attacks. In this case, a surrogate dataset must be available to the attacker to pre-train this generative model that is later used in the attack strategy. A key takeaway regarding attacks that leverage these surrogate datasets is that the real-world applicability largely depends on how closely the surrogate data matches the client's data. This is because when a high degree of similarity is required for the attack to succeed, the practical feasibility of these attacks may be limited, because we can have some application when surrogate data are not available or it's difficult to collect high quality surrogate data. This can be the case of medical application, for example. And a systematic analysis of this dependency is still missing in the literature, so we are highlighting a gap that needs to be addressed. The third category of attacks that we have identified is the analytic-based gradient inversion attacks that are mainly performed by an active server that distributes a manipulated model to the clients, causing the model updates to exhibit some specific properties that facilitate data reconstruction. The three main subcategories identified are the closed form attacks, the gradient specification attacks, and the gradient isolation attacks. And some key takeaways regarding analytic-based attacks is that historically they were considered impractical due to their high detectability. However, some recent advancements, some recent attacks have introduced more sophisticated techniques that achieve effective data reconstruction while using model modification that may be harder to detect on the client side. So as a result, the practical threat posed by these attacks in the real-world federated learning system may be increasing. In this figure, you can see an example of the table included in our work, in which we present our categorization of gradient inversion attacks. For each work, we have reported the year of publication to analyze the temporal evolution of gradient inversion attack, and we list all key factors that impact attack effectiveness and the threat models of the attack with respect to the threat models that we have previously identified. In the last column, if an open source repository is available for a given work, we provide a clickable hyperlink into document. Our third contribution concerned the defensive measures against gradient inversion attacks. In this case, we have identified two main families of defensive measures. In this presentation, I want to analyze the defensive measure by analyzing the points at which a defensive measure can be applied. And we have three main points: defensive measure that can be applied on the client side, defensive measure that can be applied during the aggregation phase, so these defensive measures are applied collaboratively among clients, and the defensive measure applied on the server side. If you analyze the first categories, so those applied on the client side, the first type of defensive measure that can be applied are the input modification. So in these methods, the clients basically alter the input through some specific preprocessing operations to balance protection against a gradient inversion attack while preserving model utility. Typically, this kind of defensive measure may have an impact over model utility, and we have noted how some of the methods proposed in the literature have later been bypassed by subsequent adaptive attacks. The second kind of modification on the client side may be the model modification. So in this case, the client locally modified the model itself to protect against gradient inversion attacks. Typically, this kind of modification are designed to make it difficult for the server to compute accurate gradients from the shared model, and this direct hinder the success of gradient inversion attacks that are highly based on gradient computation, like the optimization-based one, and for example also the latent space optimization one. However, almost all the defenses in this category have not yet been evaluated against modern gradient inversion attacks. The third type of defenses that can be applied on the client side involves the client that locally modify the model updates to provide protection against gradient inversion. The most effective measures in this category are based on local differential privacy approaches, and this kind of defenses also offer a formal guarantee of protection based on well-defined framework of differential privacy. However, the main drawback is that local differential privacy can significantly compromise model utility, especially when applied by all the clients in the federation. In the second category, we have the defensive measures that are applied collaboratively among clients during the aggregation phase. The main goal of this defensive measure is to protect the individual updates while allowing the server to see only the aggregated results, so the aggregated update to update the shared model. This approach are based principally on multi-party computation, secure multi-party computation protocol, and so it requires that all the participating clients are trusted and apply the protocol in the right way. And the main drawback of these defenses is the additional communication and computational overhead that they introduce with respect to traditional federated learning architecture. The third class of defensive measures are those applied on the server side and typically involve approaches based on central differential privacy, where the server apply differential privacy to the aggregated update. However, here we must trust the server, who is at the same time the main threat actor for gradient inversion attacks. So this class of defenses, so this is the main limitation of this defenses when dealing with gradient inversion attack, where the server is considered as the main threat actor by almost all the work in the literature. In this figure, you can see an example of our table for defensive measure, and here, with respect to the attack, we have also evaluated the robustness of each defense with respect to the previously identified threat models. This is the meaning of the threat models column, in which we can see some colored bullets with respect to threat models that we have previously identified. We have also indicated the main intuition and the main weakness of each methods, and we have indicated whether any of the defensive measures have been bypassed by subsequent attacks. In the open source column, also in this case, we have indicated a clickable link of the open source repository when available for a given work. Our fourth contribution concerns the evaluation metrics that can be used to assess gradient inversion attacks in the context of image data. In this case, we have provided a novel taxonomy of existing evaluation metrics for gradient inversion attacks by dividing them into two main categories, the image similarity based and the image recognition based. For each metric, we have identified if it's based on deep learning model or not, if it's privacy specific or not, so if it's a generic metric used to evaluate image similarity, or if it's a specific metric used to evaluate approximate reconstruction of images, as in the case of gradient inversion attacks, and we have highlighted the key aspect evaluated for each metric. A key takeaway regarding the evaluation metrics is that for threat models from A to E, the privacy-centric metrics are essential for accurately assessing privacy leakage and also the effectiveness of defensive measures against gradient inversion attacks. And relying solely on traditional image similarity metrics can be problematic, as they may underestimate the privacy risk associated with approximate input reconstructions. Our fifth contribution concerns the open challenges and future research direction that we have identified during our review. Specifically, here I report some of the future research direction identified, and some of these are also related with respect to the takeaways that I have presented during this presentation. Specifically, we note how most research focuses on image classification, leaving attacks that target other vision tasks largely unexplored. We note how client-side defenses against stealthy active adversary are lacking, and the systematic analysis of distribution shift between surrogate data and real data for attacks that leverage additional dataset is missing in the literature. And finally, we note how current privacy metrics may not fully capture the risk of approximate reconstruction, so highlighting the need for privacy-centric evaluation metric, as we have discussed earlier in the takeaway about evaluation metrics. For all the takeaways and insight developed in our work, we refer you to our full paper. And for any question or further discussion, please feel free to contact me at the email address shown on the slide. Thank you very much for your attention.